So our next speaker is Dr. Silverio Martínez-Fernández, and he is from the University of Politécnica de Catalunya, BarcelonaTech. And Dr. Silverio is an assistant professor at UPC, BarcelonaTech, since January 2020, and his PhD in computing, and he will talk to us about developing and operating green AI-based systems, software engineering approaches, and challenges. So the floor is you, Dr. Silverio.
Thank you for the introduction and also for the invitation to give this keynote. So I hope you can see the screen and hear me okay, otherwise just let me know. So we saw a very nice keynote on what AI can do for software engineering, and now we are changing the direction towards what software engineering could do for AI systems. So we will see mainly 3 points during this keynote. The first one is what are AI-based systems, and we will see how to develop and operate them. Then, as I was saying, which software engineering approaches can we apply in AI-based system projects? And third, a matter that it's requiring our attention in our research group, that it's what is the carbon footprint of AI-based systems training and inference. So let's start. There are many advances due to increased computing processing power, larger data sets, and better algorithms, and we are in the so-called rising wave of deep learning. So we can find AI-based system in two shapes, software-based. So we can see voice assistant, image software analysis, search engines, and so on. So for instance, we see an example in the slide of a translator that relies on deep learning. And we can also see it in an autonomous form, so in embedded systems, like could be applications for the Internet of Things or for autonomous driving. So we can think what is the architecture of this type of system. So there is a very famous paper from 2015 that was arguing that even in this AI-based system, there is a huge dependency of AI and machine learning. The code belonging to that part could be very small. So we can see in the image only a very tiny black box that could be the the machine learning code, but still we need the rest of software components like data collection, monitoring, serving infrastructure, and so on. So here, mainly two messages. Good software engineering practices still apply. So we should avoid to incur in technical debt, like not following a modular design or all the good practices that we know in software. So what we find? Why we find these problems? So the thing is, for developing AI-based system, we need two perspectives from two different disciplines. Data scientists and software engineers. So in software engineering, we are used to write logic as program code. And in data science, it's a bit different. We learn from data, and the system behavior is inferred from the training data. Okay, so let me introduce a bit these two perspectives isolated. For the data science perspective, we can find the well-known standard as CRISP-DM with a workflow or a pipeline very well established. So for instance, in the case of CRISP-DM, starting in business understanding, data preparation, modeling, evaluation, and deployment. Okay, so we see that in these pipelines and data science standards, there is a focus on the data set in training and evaluation. So for instance, during the modeling and the evaluation phases. And there is plenty of exploratory work. So this is where we work, for instance, in a Jupyter notebook, and we are just understanding the data, exploring it, and there are many studies that uh, show that up to 80% of the work in a data science project is only dedicated for the data understanding and the data preparation. So there is a lot of work in feature engineering and modeling techniques. And the focus is building just an AI model or machine learning model or deep learning model. Okay. And we focus on prediction accuracy. So if we are predicting how, for instance, a traffic sign, we want to be correct as many times as possible. So this would be the prediction accuracy. And more, we realize that there are other key qualities that we need to pay attention, not only accuracy, but also robustness, ethics, explainability, and so on. I will come back to there in a few slides. And then we see the software engineering perspective. So here we are not focused on building an AI model, but a complete software product. And we can find in all the software development approaches, like it could be DevOps, trying to accelerate the delivery of software changes, as well as in Agile, that there is always a balance between requirements, resources, and release time. What we have done very good in the software engineering community is considering quality attributes and technical excellence. So for instance, try to address non-functional requirements and quality attributes with technical, well-done architecture. And also, for instance, in the case of autonomous car, we need to follow very rigorous test and certification standards that they are not ready yet still for AI models, or they are starting to be ready. There is a lot of focus in the last decades on continuous deployment. So it's not like following like what in waterfall methodology. And there is a lot of research on maintaining a software product, so evolving the product over long periods. So once we have seen these two perspectives, this could be an example of joining both data science and software engineering for the sake of developing and maintaining AI-based systems. So let me introduce a bit this process. We see the two first cycles coming from that it would be where a data scientist would be working. They are data management and modeling. So in the data management, we need to prepare, label, and collect the data. As far as we can, we shall semi-automatize this process. So for instance, building connectors to gather this data, trying to clean up with scripts that could be reproducible and so on. And once we have the data ready, then we start the modeling cycle. Here we start with the feature engineering. What are the most relevant features, training, and evaluating. To do this, borrowing software engineering practices, we could do experiments, as it is the case, for instance, in platforms like MLflow. So every time that we train a model, saving the data set, the configuration of the parameters, and the evaluation. And in the evaluation, it's very important not focusing only on the accuracy, but also we will see later energy efficiency and other quality aspects, performance, and so on. Okay, so normally we do the modeling cycle as many times as we need until we are happy, let's say, with the evaluation, with the accuracy, and so on. And then we start the deployment into the whole system. So we have a model. So for instance, a neural network predicting a traffic sign. And then we need to deploy it into the whole system. That could be an autonomous car. Okay, so here is where we start the software engineering perspective. So software engineers, they work in the development of the whole system. So they need to do integration test of the machine learning model in the whole system. And then, well, we follow the normal process of releasing it and deploy it and operation. Ideally, in operation, we will be monitoring the AI system. So in the case of autonomous car, that it's behaving correctly. In the case of, for instance, the translator that we saw of a web application, that the translation is correct. But we should always have opportunity in case we learn new data. So to gather new data and then retrain the model, and then all the cycle restart again. So it's not something we do once, but that we should also think on the maintenance of this product due to concept drift and so on. So let's see it in a sample that we did recently. So for instance, a mobile application that we can take a picture and then of a traffic sign. So for instance, a stop sign, and then tell us the traffic sign that is there. No, so it would be an example, a first example of embedded application for autonomous cars. So what is the development process we follow? So we started with the data set, many images from traffic signs from from Germany. So this is a data set that if you are interested, you could use. And we start modeling different neural networks. So for transfer learning, mobile nets and ResNet, also building our own neural networks with different amount of parameters. So we call them small, medium, and big. And once we are happy with the model, so remember this modeling cycle we were mentioning before, then we deploy this model in the Android application. We do the integration test. We see that the whole system, in this case, a mobile application, is working. And then we go to operation. And as I was saying, for instance, it was our case that we were using a dataset from Germany. So once we had a very first version, we were gathering also images in Barcelona and increasing our data set and retraining again for the generalization of the approach. Okay, so this is, let's say, the main 4 cycles of AI development. And we can see also this in industry. So it could differ a bit, but in essence, it's the same. So the main message is that we are mixing data science and software engineering processes. So for instance, in this example, we see here all the software engineering part, application composition, application testing, DevOps, and so on, requirements, application design, okay, so the software engineering cycle. And then in the other hand, the data science cycle for preparing the model. So this is an example from IBM. And then we can also see it from Microsoft here with a stronger focus on data science. So we see all the activities, all the pipeline for the data science part, feature engineering, model training, model evaluation, and so on. But we cannot forget about the deployment, about the software engineering part, and also monitoring all the quality aspects and so on. Also, well, deploying the AI model as web services, as intelligent applications, that would be AI systems, and so on. So this is let's say, the current state, the first point of the presentation. And now I would like to introduce which software engineering practices we could use in this type of projects, in AI-based systems projects. So there is a lot of recent literature on this topic. One very good example is this one from Alex Servan et al., that they define a set of software engineering best practices for developing AI systems. They have grouped all these good practices into 6 categories: governance, data, team, training, deployment, and coding. So we can recognize categories like coding for test automation, continuous integration or deployment, automated deployment, and so on, that we see that in previous standards like CRISDM or SEMA, they are lacking, or at least there is not clear guideline of how to do it. So this is why software engineering could benefit a lot this type of project. So based on this scenario, what we did was a systematic literature review with some colleagues also from Germany, from Kaiserslautern and Stuttgart. It's published in Tossen. You can see this paper. And what we found was 248 software engineering studies that apply some software engineering approach for AI systems. So we classify them following the SV book knowledge graph in software requirements, design, and so on. So in the next slide, I will introduce a bit what we can find in each area. So for instance, in software requirements, there is a lot of focus on non-functional requirements or quality attributes that are new and specific for AI. So for instance, in the ISO standard 25010, that is the most used one for the qualities of software systems, there is not a complete extension, for instance, of inexplainability. No? So just to put an example, if we think in some AI software that is helping a doctor detecting cancer in an image, it's important not only to detect correctly the cancer, but also in case the doctor see it and use it, that she or he can explain to the patient why this or how this cancer was detected with the AI solution. So this is an example of explainability that everyone understands how the AI model and the AI system behave. Yeah, and then we see the typical one: safety, functional correctness, and so on. So safety is the most popular one, and this is due to the undeterministic context of AI models. As we were saying, in traditional software, we program written code, and in AI models, we learn from the data, and it's more challenging to build the test case. So there are several specification annotation approaches to reduce ambiguity. And what we realize, okay, you see that there are many approaches for instance, 74 for safety, but there are very few covering the whole requirement engineering process for AI. Still, you can find it. There are a couple of them. Okay, regarding software design, here the research that we have found is design strategies to cope with specific quality attributes. So in the image, we can see that the most popular ones are dependability and safety. And for instance, for others like explainability and transparency, ethics and trust, they are very well known in the community, but still they are not that mature. And they need to be very specific for the type of AI model. So very specific for natural language processing, for computer vision, well, depending on the AI. Then there are several AI infrastructure proposals like sharing models as microservices or reasoning on the architecture for edge versus cloud and so on. But however, at the system level, there are very few proposal patterns. So for the whole AI system level, there are not yet reference architectures explaining all the options, or for instance, deployment options you may have. Okay, regarding software construction, there are starting to be many tools and platforms. That it could be the case of MLflow, or some more industry like Comet and so on. but still they are emerging. So they are new. They have, let's say, 1-2 years old. And there are many practice studies from industry that are reporting changes and guidelines of this type of system. So this is showing that it's a very hot topic also for industry, and it has a very big application. And what we can find, where we can find most of the research is in software testing. So here there are more than 1/3 of the studies were just about testing. And okay, they specialize in test case generation and test case selection. There are also many papers about which testing metrics we should use. And for instance, an example would be in the traffic sign example that we were following before. So for instance, how just generating an adversarial input, changing pixels, could lead to a very different outcome, and therefore could be a very huge vulnerability to hack this system. Software maintenance is by far one of the most important ones, because as we were saying before, it's not only about executing these 4 cycles, data management, modeling, development, and operation, but also about coming back and executing everything again, doing software maintenance with new data, dealing with concept drift, running from other AI-based systems, and it's distributed, and so on. So there is many open challenges here that deserve more attention. And there has been a few studies on bugs and debugging AI-based systems. And then for the software engineering process, where we saw a few examples of from IBM and Microsoft before. So many of them are done in an ad hoc manner based on early experiences of making AI-based systems. So this is very emerging topic, very strong. There are many people working on this, but still there is no, let's say, a standard way to do it. So yeah. And if we come to software quality, here mainly, for instance, for in the case of autonomous cars, the ISO 26262 is evolving towards SOTIF. So the idea is to include the verification of AI components, and also a lot of work of evolving the ISO 25000 series to include quality aspects that are relevant for AI systems. And here, let's say the target would be that in case we have an AI system, we can really certify that it has the quality needed so that it can work in operation and so on. Okay, so this was the second, let's say, part of my talk. As I said, you can see all the details in the journal article, and well, I can elaborate a bit more in the question if needed. And I would like to go just to a subset or to one topic of all this software engineering for AI research, that would be sustainable software engineering or green AI. So just to put a bit the context, so large artificial intelligence and software companies shall follow energy efficiency regulations as any other company, industry, and so on. So in the case of Europe, the European Union has agreed ambitious targets for greenhouse gas emission reductions. And even by 2050 to reach a climate neutral economy. And here it's our opportunity as software engineers trying to optimize the energy efficiency of software systems. So there are a few studies that claim and show with empirical data that the IT system alone already consume 10% of global electricity. So this is from the data centers where all the software run. And even this could get worse because there is more and more the use of AI systems. And this could, in the very worst case, in the very worst estimation, let's say, led to a 28% of increase in energy consumption of data centers by 2030. So there is a clear need for an ecological behavior, and this would be to mitigate the impact also of software and AI systems in climate change. Okay, so sustainability is a very overloaded word. It's being used more and more. So this is why I was talking a bit more about green AI, just to make clear the idea that we need to optimize the training process of AI models, use a more efficient use of data. So more data does not necessarily implies better AI models. So we need to think of smarter ways to train our AI models. I'm here just to acknowledge that AI system could play a dual role. So they are positive in the way that they can help reduce the effect of climate crisis. So, for instance, modeling the climate change predictions or learning based on data how we can mitigate climate change. And what we are focusing also is that still AI systems are themselves a significant emitter of carbon, and we need to make them energy efficient. So I will discuss these two roles. So, for instance, how software engineering could be good for energy efficiency of AI systems. So, for instance, in the guidelines I was mentioning before, that companies shall follow to report on their climate impact. So, for instance, they need to report as key performance indicators direct greenhouse gas emissions, or also the total energy consumption of the activity. And here, what we could do is using all the tools that we have in software engineering and also business analytics. So to leverage all these strategic indicators and quality management for greenability quality models. So, for instance, a project in which we work towards this direction just in software analytics was QRapids, and we could reuse this software like to do some key performance indicators for green AI, and then ideally the same as we have in our house appliance like fridge and washing machine and so on. So an energy certification of the software system that we are using. So this could be an idea. And then on the other way around, it's okay, the carbon impact of AI system in numbers. So just to see how important is this problem or this could become. So here we see, for instance, using a car from the States in average, the car for all its lifetime, it could have this carbon footprint. And for instance, training a very big transformer with neural architecture search, it's much more the carbon impact of this train. So this might be hidden to us because it's running in data centers and so on, but it requires a lot of energy. And here we see there are studies that argue the exponential energy that is needed to train, for instance, AlphaGo 0 in comparison with other previous models. Okay. Okay, so there is also very popular paper by Roy Schwartz that argues or compare rate AI, So this is the AI that it's just looking towards very good accuracy, and it implies very extremely high cost on executing model on a single sample, size of retraining data set, number of hyperparameter experiments, and so on. And what the software engineers we should start to think about and continue to think about is how we can model and develop these AI systems um, so that we demand less computational power. Okay, so this is in contrast to red AI, what we would call green AI. So as I was saying, the more data, it doesn't imply the best system and the more energy. Okay, so as a very starting point, there is much that can be done to develop tools to quantify the carbon cost. Currently, there is an absence of a standard of measurement, so it's discussed so far in recent literature that one appropriate, for instance, metric would be the fraud point operations, because, well, we could compare between different hardware infrastructures. But what is clear is that in our AI papers, we need to start tracking and reporting the energy consumption. There are many tools, like it could be Code Carbon, that it's specific for Python, or Intel Power Management based on REPL, and so on. So this is something for the people that is working on AI system, just also considering when you do your work to track and report the energy consumption of your experiment. And I would like to show an example of what we are currently doing. So we want to see which design decisions contribute to greener AI in the context of AI mobile applications. So for instance, here we have many data sets about image classification and text classification. And what we are doing in this research is seeing if, for instance, we can get a trade-off and an optimal balance between the number of parameters and the accuracy of the model, so to reduce the energy efficiency. Also, if the architecture type, like well, BGG or ResNet and so on, can impact a lot the energy consumption of training AI models, and also the memory use. So for that, this energy could be tracked with profilers. So this is a case, and a screenshot in TensorFlow, or also for what we could use. It's not in the slides, but it's WOMeters as hardware infrastructure. Okay, so just to give a conclusion of the keynote, just 3 takeaway messages. So for the development of AI systems, we need multiple stakeholders, and the very least data scientists and software engineers. That's what I introduced. Of course, the bigger the project, you may also need more stakeholders, as it could be data management, or even always we needed the expert in the application domain. This is I didn't mention, but it's always important to have it. A second takeaway, there are many software engineering approaches for AI, so it's important to understand the difference for researchers and update the software engineering approaches, and also some areas as maintenance are not solved yet. They need research. And the third takeaway message is that we shall not forget about the carbon footprint of AI-based systems. And remember to track it, report the energy consumption of the system. And if you do research, try to optimize AI models so that they require less energy. So that would be all from my side. Thank you for listening. Thank you for the invitation as well. Very happy to be in this conference. And hopefully next year I could join in person. If you have any questions. I cannot hear. I'm afraid I cannot. I cannot hear. I see people is asking questions, but if you could write them in the chat. No. Okay, no. Okay, so I see one in the. I don't know if it's this. In this, if this is the question. So, okay, in reference to the need for an ecologic behavior, isn't the integration of AI more and more software counterproductive because each new model being integrated into a particular piece of software needs to be trained, which means exactly. So this is exactly the point. And what we shall try to do is understanding the impact of training these models, because it doesn't need to be bad. So there are many recent research. So now people is not only focusing on accuracy, but doing the trade-off with energy consumption, and and this can be done. So it requires new architectures, but this can be done. Very good question, by the way. Yeah, I'm very sorry. I see that you are asking things, so I can read the chat. If you write in the chat, I can reply. Okay, so I see another question by Askan Sami. So could you explain the mobile app that you improve it based on Green AI concept? Yeah. So what did you do and how much improvement did you obtain? Okay,
you can
so
follow up
there
on
was.
these questions
Now
on
I
the
can hear.
yeah, and we
Now I can
have
hear.
here one question from the venue at Egypt here.
Silverio, thank you for your insights, information related to this hot topic, AI. One short question. So you see that AI and software has to be put together, so to speak. And I saw that you have to bridge the data engineer with the software engineer. Who will make the first step? Should we learn, the students from the data science, more software engineering, of the opposites, the software engineers, more data science? So how can we bridge that? How you see that?
So I think both directions are correct, and we can see it in this keynote and in the previous one. So I like a lot reflection by Christian Kessler from Carnegie Mellon University, that he says this is an educational problem. So for instance, what they are doing in the subject there, and also we are doing with people with University of Bari and our own university, is teaching in data science programs software engineering approaches, and in software engineering programs machine learning approaches. So I think it's educational, and it depends a bit in the profile, whether, in my opinion, you should just get a grasp of the other discipline. Thank you for the question.
Yeah. Okay, Dr. Silverio, thank you very much for your time and for your insightful talk.